Welcome! In today's session, we'll be exploring an interesting problem from LeetCode, problem number 1750, titled Minimum Length of String After Deleting Similar Ends. We'll dive into the problem, analyze a brute force approach, and discuss its complexities. Let's get started. In this problem, we are given a string S that consists of only three possible characters, A, B, and C. We can perform an operation where we delete both the first and last characters of the string, but only if they are the same. The goal is to determine the minimum length of the string after we have performed as many of these operations as possible. For the input format, we are provided a string S where the length of the string is between 1 and 100,000 characters. The output is a single integer that represents the minimum length of the string after all valid operations have been executed. Let's now look at an example to understand this better. If the input string is S equals CA, the first and last characters, C and A, are different. Since no operations can be performed, the minimum length of the string remains 2. Now, consider another example where the input string is S equals cababack. Here, the first and last characters are both C, so we can perform an operation to remove them. This reduces the string to a bab. Next, the first and last characters of a bab are both A, so we remove them as well, leaving bab. Repeating this process, the first and last characters of bab are B, so we remove them, resulting in A. Finally, the first and last characters of A are the same, so we remove them, leaving an empty string. Because the string is now empty, its minimum length is 0. This example demonstrates how multiple operations can reduce the string completely. In the third example, we are given the string S equals abcaba. The first and last characters, A and A, are the same, so we remove them, leaving abcab. Now, the first and last characters of abcab are A and B, which are different, meaning no further operations can be performed. The string is left as cab, and its length, 3, is the minimum length possible. This example highlights that not all strings can be fully reduced, as operations depend on matching first and last characters at each step. With this, we can now think about the constraints and edge cases for the problem. The problem guarantees that the string S consists only of the characters of B and C, which simplifies our logic. Let's consider some edge cases. If S has only one character, no operations can be performed, so the output is simply 1. For example, A, B, or C would all result in an output of 1. Another edge case occurs when the string is homogeneous, like AAAA. In this case, the string can be reduced step by step until it becomes empty, and the output would be 0. For strings with alternating characters, such as ABC, no operations are possible because the first and last characters will always differ, so the output is the original length of the string. Finally, strings like ABA that can be fully reduced to an empty string would also have an output of 0. These edge cases help us better understand the problem and how to handle various input scenarios. To solve this problem, one straightforward method is the brute force approach. The idea here is simple. We repeatedly check if the first and last characters of the string are the same. If they match, we remove both characters and continue this process until either the string becomes empty or the first and last characters differ. For example, you start with the full string, and as long as the first and last characters are the same, you remove them. This can be done using a loop or recursion. However, there's a major downside to this approach. Since each removal operation involves creating a new substring, the time complexity can grow to O(n squared) in the worst case. This happens because each removal takes linear time, and we may perform this operation up to n times. Additionally, the space complexity is also O(n), due to the creation of these intermediate substrings. As a result, while this method is easy to understand, it's highly inefficient for longer strings. The brute force approach, though simple, has significant trade-offs. It's intuitive and easy to implement, but it becomes extremely inefficient for large inputs because of the repetitive copying of substrings. A better alternative is the two-pointer approach, which is much more efficient. Instead of repeatedly creating new substrings, this method uses two pointers to determine the boundaries of the valid substring. Here's the intuition: you place one pointer at the start of the string and the other at the end. If the characters at these positions match, you move both pointers inward until the characters differ or the pointers meet. If the pointers cross, the final string length is 0. Otherwise, the length of the substring between the pointers is the result. This avoids the overhead of creating intermediate strings and focuses only on the essential comparisons. The two-pointer approach offers significant improvements in both time and space complexity. Its time complexity is O(n), because each pointer moves through the string at most once, and no redundant operations are performed. The space complexity is O(1), as we don't use any additional space aside from the two pointers. While this method is slightly more complex to implement compared to the brute force approach, the trade-offs make it worthwhile. It's faster, more memory efficient, and handles larger inputs gracefully. By avoiding unnecessary string rebuilding, we achieve both performance and simplicity, making this approach highly effective for solving the problem. Given the strengths of the two-pointer approach, it's the strategy we chose to solve this problem. The core insight here is that the problem only asks for the length of the remaining string, not the substring itself. This means there's no need to physically modify the string. Instead, we can use pointers to adjust the boundaries of the substring efficiently. Matching ends can be ignored without affecting the relative positions of the remaining characters, and the two-pointer technique does this seamlessly. This method is efficient, with a linear runtime, and avoids the pitfalls of the brute force approach. It's also elegant in its simplicity, as it eliminates redundant operations and provides a clear, scalable solution. In comparison, while the brute force method is easy to grasp, its quadratic time complexity makes it impractical for larger inputs. The two-pointer approach is the optimal choice for both clarity and performance. To wrap up, the two-pointer approach stands out as the most efficient and scalable solution for this problem. It balances clarity, performance, and scalability, making it ideal for both small and large inputs. By focusing on adjusting the boundaries of the string rather than modifying it directly, this method achieves optimal efficiency with minimal overhead. This approach not only simplifies the implementation but also ensures that the solution remains robust across various edge cases, such as strings with repeated characters or empty strings. It's the perfect balance between theory and practice, providing a clear path to solving the problem effectively. To determine if a string is a palindrome, we need to check if it reads the same forward and backward. Examples include words like racecar and madam. The task is to design an efficient algorithm to perform this check. One simple approach is a brute force method. Here, we iteratively compare the first and last characters of the string. If they match, we remove both characters and continue the process until the string becomes empty or a mismatch is found. This method, while straightforward, involves repeated string slicing, which makes it computationally expensive, with a time complexity of O(n squared). The steps include validating the input to ensure it's a string. Once validated, we initialize the string variable, which will undergo iterative processing in the next steps. The iterative process for the brute force approach begins by checking if the string is empty. If it's not, we compare the first and last characters. If they match, we slice the string to remove these characters using S(1-1), effectively shortening the string from both ends. On the other hand, if the characters do not match, we terminate early and conclude that the string is not a palindrome. If the loop completes and the string becomes empty, this means all character pairs matched symmetrically, so we return true, confirming that the string is indeed a palindrome. The brute force approach relies on the symmetry of palindromes. By comparing the first and last characters, we systematically reduce the problem size. However, this approach has a significant drawback. String slicing creates new string objects in memory, and each slicing operation takes O(n) time. Since we perform this operation n/2 times, the total time complexity becomes O(n squared), which is inefficient for large inputs. For edge cases, an empty string is trivially a palindrome, as there are no characters to mismatch. Similarly, a single character string is always a palindrome. Depending on constraints, we might also need to pre-process the input to normalize case or remove non-alphanumeric characters. It's important to remember that strings are immutable in many languages like Python, which contributes to the slicing overhead. These limitations highlight the need for a more optimal approach. To address the inefficiencies of the brute force method, we can use the two-pointer technique. This approach avoids slicing altogether, significantly improving performance. Here, we use two pointers, one at the start of the string and the other at the end. By comparing the characters at these pointers, we can determine whether to move inward or terminate early. If the characters match, we increment the left pointer and decrement the right pointer, effectively narrowing the range of comparison. If the characters do not match, we can immediately return false, as the string cannot be a palindrome. This method is both time-efficient and space-efficient, as it eliminates the need for repeated string slicing and does not allocate extra memory. In the two-pointer approach, if the loop completes without finding mismatched characters, we return true, confirming that the string is a palindrome. This method has a linear time complexity of O(n), as we traverse the string only once. The space complexity is O(1), as no additional memory is required beyond the two pointers. In contrast, the brute force method has a time complexity of O(n²), due to repeated slicing, and a space complexity of O(n), for storing the intermediate strings. The two-pointer technique is clearly more efficient and is the recommended approach for this problem, especially for larger inputs. By eliminating the overhead of slicing, we achieve a solution that is both faster and more memory efficient. This implementation solves the problem of finding the minimum length of a string after repeatedly removing matching characters from both ends. The process involves two pointers, left and right, that start at the beginning and end of the string, respectively. The algorithm operates in a loop while the two pointers have not crossed and the characters at both ends of the string are equal. When a match is found, the algorithm captures the character to be removed and adjusts both pointers inward. The left pointer moves forward as long as it encounters the same character, and the right pointer moves backward for the same condition. This ensures that all consecutive matching characters at both ends are removed in one iteration. Once no more matching end characters exist or the pointers cross, the loop exits. The remaining length of the string is calculated as right, left plus 1. This result represents the minimum length of the string after all valid removals. The algorithm runs efficiently in O(n) time since each character is processed at most once. It handles edge cases like strings with no matching ends, strings where all characters are identical, and empty strings seamlessly. This Java implementation mirrors the logic of the Python solution for LeetCode problem number 1750, minimum length of string after deleting similar ends. The algorithm uses two pointers, left and right, to traverse the string from both ends, removing matching characters until the pointers meet or cross. Key differences in Java include explicit type declarations and the use of char@ to access characters in a string. The method ensures that the solution is concise and efficient, directly returning the length of the remaining substring after processing. To solve this problem, we start by initializing two pointers, left at 0, which represents the start of the string, and right at 3, which is the last index of the string since its length is 4. The input string here is abca. First, we check the characters at both ends of the string, s left is a and s right is also a. Since these characters match, we proceed to remove them. To do this, we move the left pointer forward as long as s left remains a. After incrementing left by 1, it points to index 1 and the substring becomes bc. Similarly, we move the right pointer backward while s right is a, decrementing it to index 2. The substring still remains bc because the matching characters at the ends are now removed. At this point, we check the characters at the updated left and right pointers. S left is b and s right is c, and since these characters do not match, we stop. The remaining substring is from index 1 to index 2, which has a length of 2. Therefore, the final output for this example is 2. In this example, the input string is abca. As before, we initialize left at 0 and right at 7. The characters at both ends are a, so we remove them. We increment left to index 2 as long as s left is a, and the substring becomes bccb. Similarly, we decrement right to index 5 while s right is a, and the substring stays bccb. Next, we check the updated ends, s left is b and s right is also b, so we remove these matching characters as well. Moving left forward while s left is b increments it to index 3, leaving the substring cc. Moving right backward while s right is b decrements it to index 4, so the substring remains cc. We now check the characters at the updated pointers, s left is c and s right is also c. Since they match, we remove them. Incrementing left to index 4 makes the substring empty, and decrementing right to index 3 confirms that left right. At this point, all characters have been removed, and the length of the remaining substring is 0. Thus, the final output for this example is 0. Here, the input string is Quebec. We initialize left at 0 and right at 4. The characters at the ends are C, so we remove them. Moving left forward while S, left, is C increments it to index 1, resulting in the substring ABA. Similarly, moving right backward while S, right, is C decrements it to index 3, and the substring remains ABA. Next, we check the updated ends, S, left, is at and S, right, is also A. Since these characters match, we remove them. Incrementing left to index 2 leaves the substring B, and decrementing right to index 2 confirms the substring remains B. At this point, S, left, is B and S, right, is also B, but since left is now equal to right, we stop. The length of the remaining substring is 1. Therefore, the final output for this example is 1. The time complexity of this solution is O, n, where n represents the length of the input string. Let's break this down step by step. First, we have the outer while loop, which runs as long as the left pointer is less than the right pointer and the characters at both ends of the string are equal. This ensures we process the string only as long as there are matching characters at the boundaries. Within this loop, there are two inner while loops. The first inner loop moves the left pointer forward for as long as consecutive characters on the left match the current boundary character. Similarly, the second inner loop moves the right pointer backward for as long as consecutive characters on the right match the same boundary character. Importantly, each character in the string is processed at most once by either the left or right pointer as they move inward. Since no character is revisited, the total number of operations is directly proportional to the length of the string, making this an O(n) operation overall. To solidify this, consider a mathematical perspective. Each character in the string is visited exactly once by the left pointer as it moves forward and once by the right pointer as it moves backward. This results in a total of n pointer movements, confirming that the time complexity is O(n). Now, moving on to space complexity. The solution operates in place and requires only a constant amount of extra memory, which is O(1). The pointers left and right are simple integer variables that track the current boundaries of the string. Additionally, we use a variable char to temporarily store the current boundary character being processed. These are fixed memory allocations irrespective of the size of the input string. No additional data structures, such as arrays or stacks, are used, and we don't create any copies of the string. As a result, the space complexity remains constant at O(1). When we compare this optimized approach to a naive solution, the difference becomes even clearer. A brute force method might involve repeatedly slicing the string to remove matching characters from the ends. Each slicing operation creates a new substring, which increases both time and space requirements. Specifically, the time complexity in the worst case would become O(n squared, since we would be creating new substrings in each iteration. Additionally, the space complexity would increase to O(n) for storing these substrings. In contrast, the optimized approach avoids this overhead entirely by using two pointers to track the boundaries of the string. By working directly on the input string without creating copies, the time complexity is reduced to O(n), and the space complexity to O(1), making it significantly more efficient. Now let's analyze the best, average, and worst case scenarios. In the best case, the first and last characters of the string are different. Here, the outer while loop doesn't execute at all, and the algorithm simply returns the length of the string. This results in an O(1) time complexity. In the average case, the algorithm processes a few matching characters at both ends of the string before terminating. The number of operations remains proportional to the length of the string, leading to a time complexity of O(n). The worst case occurs when the string consists entirely of identical characters, such as AAAAA. In this situation, the algorithm processes all n characters through the inner loops, resulting in a time complexity of O(n). In conclusion, the optimized solution is both time efficient and space efficient, achieving O(n) time complexity and O(1) space complexity. This improvement over naive methods is due to the use of two pointers, which ensures each character is processed only once, making the algorithm highly scalable for large inputs. When solving this problem, there are several common mistakes to watch out for. First, ignoring edge cases like empty strings or strings with just one character can lead to runtime errors. For instance, if you attempt to access the first character of the string without checking if the string is non-empty, you might encounter an index error. To prevent this, always handle these edge cases explicitly before diving into your main logic. Next, if the input string is already a palindrome, some solutions may still perform unnecessary computations, such as additional checks or recursive calls, which waste time. A better approach is to include a quick pre-check for palindromes and handle them as special cases. Finally, overcomplicating the algorithm is another frequent issue. For example, using nested loops or extra data structures when a simpler two-pointer approach could solve the problem more efficiently. Simplify your logic and analyze the time complexity to ensure your solution is both correct and optimal. Another common challenge is managing indices correctly, especially in a two-pointer approach. Off-by-one errors can occur when transitioning from one character comparison to the next. To avoid this, carefully test boundary conditions and use debug tools like print statements to verify that indices are being updated correctly throughout your implementation. Recursive solutions can also be tricky, particularly when defining the base case. If the base case is not implemented correctly, it can lead to infinite recursion or incorrect results for smaller input cases. Therefore, always take the time to clearly define the base case and test your solution with minimal inputs to ensure everything works as intended. Now let's talk about some valuable insights for interviews. The two-pointer technique is a powerful tool that can be applied to many string problems, and interviewers often look for candidates who can identify when this approach is appropriate. Additionally, while it's helpful to start with a brute force explanation to build intuition, you should quickly transition to the optimal solution, clearly outlining your thought process along the way. Demonstrating the ability to test edge cases, such as empty strings, single characters, and strings of varying lengths, is another critical skill. Lastly, be prepared to discuss space-time trade-offs. Whether you're using an iterative, recursive, or dynamic programming solution, you need to explain when the extra space or time complexity is justified. To further enhance your understanding, you might want to explore related problems, such as longest palindromic substring, palindrome partitioning, or valid palindrome 2, as these often share similar techniques and concepts. There are several alternative approaches to solving this problem, each with its own trade-offs. The two-pointer approach is one of the most efficient, with a time complexity of O(n) and a space complexity of O(1). It's simple and highly effective for problems that involve checking palindromes. However, it may not be as flexible when dealing with substring manipulations. Another option is the recursive approach, which also has a time complexity of O(n), but requires O(n) space due to the recursion stack. This method is easy to implement for problems with overlapping subproblems, but the extra space overhead can be a drawback. Lastly, dynamic programming is a more comprehensive approach with a time complexity of O(n)² and a space complexity of O(n)². While it's ideal for problems that require finding all palindromic substrings, it can be overkill for simpler tasks like basic palindrome checks. String reversal is another alternative approach worth considering. In this method, you reverse the string and compare it to the original. It has a time complexity of O(n) and requires O(n) space to store the reversed string. The primary advantage of this approach is its simplicity. It's straightforward to implement and understand. However, the trade-off is the additional space required to store the reverse string, which might not be ideal for scenarios where memory usage is a constraint. Overall, it's a useful method to keep in mind when simplicity and readability are priorities over space efficiency. Great job! To recap, we analyzed a brute force solution to the problem minimum length of string after deleting similar ends. Remember to focus on edge cases and optimization when tackling string problems. Thanks for joining, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!